Assalamu alaikum. Today we'll be starting a new section that is atomic physics. In this section, we have two chapters. One is atomic physics, where we discuss the structure of an atom, and the second is radioactivity, where we discuss um, nuclear radiations. So, first of all, I'll be sharing for nuclear atom. So, in this, we'll be discussing the structure of an atom, and later on it will be applied to different disciplines of sciences such as engineering, material science, and pharmacology. And first off of this section means nuclear atom. Will be discussing the theory in which structure of an atom was given. Now, most of us have heard about that atom is the basic structure of all the substances, and atom itself has subatomic particles. For example, there are three basic particles which are known as proton, neutron, and electron. Nowadays, there are even more classifications in this atom. Even neutron and proton are made up of fundamental particles, but electron is a fundamental particle itself. But we'll be limiting our discussion to these three subatomic particles. So, and we have been discussing some applications for these particles. For example, we have discussed the phenomena of ionization, static electricity, and flow of current in a circuit. And then we have discussed thermal conduction and electrical conduction in metals. We'll also be discussing thermonic emissions. So all of that is uh, depending upon these subatomic particles, specifically electron. So it has its um, uh, learning outcomes in CI syllabus. So it has structure of atom and Rutherford's experiment and composition of the nucleus and its atomic and mass number, and then its notation, and then we'll be defining isotopes, and we'll also be applying these isotopes to like isotopes of uranium. So we'll be discussing that too. Okay, so in early 1900s, Rutherford with his two assistants, Geiger and Marston, they performed an experiment. So I'll first tell you the apparatus here. So we have a source of a radioactive emission here, that is alpha particle. Now we have not discussed alpha particle yet, but alpha particle is basically equivalent on of a helium nucleus which has two protons and two neutrons. So it means it is a positively charged particle. Okay, so it is positively charged and it is heavier particle. So that source of alpha particle which can only emit in one direction. Okay, so waves can be, or sorry, uh, alpha particles can leave from this source only in one direction, and in front of it we have placed a thin gold foil. Now I hope you know, all of you know, that gold can be drawn into thin sheets, very thin sheets, and it is so thin that its width is few hundred atoms. So it's malleable, so it has the property to be done that way. And then we have a covering of this apparatus, which is some fluorescent screen or photographic film, or we can have detectors also on all the sides. So what happens whenever a particle hits that screen, there is a glow which can be counted and which can be observed. So alpha particles are hitting that gold foil at the center, and you can see that most of the particles are passing straight. Some of the particles are being deflected at smaller angles, and only a few of the particles are being deflected at larger angles. So have to have a better picture, we'll be discussing this screen. Yes. So for example, this is an atom. So you can see most of the alpha particles, these are alpha particles. These are, yes, it's written alpha ray, alpha particles, which are hitting straight, passing straight, and there is no deflection observed. So few alpha particles are being deflected at smaller angles, and very few, you can observe this one, very few which are being deflected at larger angles, means those alpha particles are experiencing some head-on collision. And the particles which are being deflected at smaller angles, those are deflected like if this was an alpha particle and it was positively charged. So those particles may be passing near some positively charged entity. So we'll be discussing the observation of Geiger and Marsden. So what does it say? Nearly all alpha particles, means most of the alpha particles, pass straight through. So that tells us that atom is almost empty. Second, a few alpha particles deflected through smaller angles. So it means there is something which is in the foil. Third, now the continuity of this second observation, that a very few particles rebound through very large angles. Now that rebounding can only be possible if there is a heavier entity there. For example, you have placed a basketball and you are throwing another ball on it. So it can only be deflected at a larger angle if thrown ball is being rebounded from a heavier ball. Okay, so it means there is some heavier entity at the inside that gold foil. And last thing, that rebounding can only happen if that entity is positively charged, because alpha particle was positively charged. Okay, so the suggested model is this one, that we have some heavier nucleus inside an atom, and there are electrons around that nucleus, and there is a noticeable space between electrons and that nucleus. And nucleus is very small in size. Why very small? Because very few particles were deflected at larger angles. So Rutherford concluded that atom has a tiny massive core called nucleus. The nucleus has a positive charge. Electrons are particles with negative charge. The empty space between the nucleus and the electrons takes up most of the volume of the atom. So if we compare sizes, so almost atom is 10 exponent minus 8 centimeters, and nucleus is 10 exponent minus 12 centimeters. So you can differentiate between the size of the nucleus and atom. Then size of the proton, that is almost 10 exponent minus 13 centimeters, and size of the electron is even smaller, 10 exponent minus 16 centimeters. Then there is another subatomic particle of which the protons are made, those are quarks, so we won't be discussing that. Okay, now number of electrons and number of protons are same in an atom if an atom is neutral. So electrons having negatively charged and protons having positively charged at the nucleus of an atom, number of both will be same for a neutral atom. So we define two terms here, that is the atomic number and the mass number of an atom. So number of protons at the nucleus, that is known as atomic number, that determines the chemical properties of the atom, and number of protons and the number of neutrons is the mass number of the atom. So it's displayed, the mass number is displayed with the symbol capital A, and atomic number is displayed with the symbol capital Z. Mass number is top left corner, and atomic number written at the bottom left corner. Okay, so with this notation, for example, we have written here helium, He. 2 is the atomic number, which gives the number of protons here. So if number of protons are 2, the number of electrons will also be 2. Mass number is given 4, so that means number of protons 2 here. So 2 will be number of neutrons. So 4 is number of protons plus number of neutrons, that is 2 plus 2. Okay, after that, for example, if we have written for carbon, that is atomic number written 6 and mass number written 12. So number of protons 6, number of electrons 6, and number of neutrons are also 6. For chlorine, it's written 1735. So number of protons are 17, and number of neutrons here will be 18. Okay. Okay, now we'll be moving on to isotopes. Now, two atoms with the same proton number may have different number of neutrons. So chemical properties for those two atoms will be same because chemical properties are depending upon the number of protons. So if two atoms have same number of protons, their chemical properties will be same. But if they have different number of protons, if they have different number of neutrons, then those two atoms will be known as isotopes of the same atom. Okay, moving on, we can have some examples for that. Now, one very common example is of um, hydrogen. So there are three isotopes in front of you. One is protium, the other is deuterium, and the third is tritium. So 1H1 stands for number of proton 1, number of neutrons 0, number of electrons 1. 1H2 means number of proton 1, number of neutron also 1. So mass number is 2. Tritium means number of proton 1 and number of neutrons 2. We'll also be discussing for uranium because we'll be discussing that in detail later in our chapter. So uranium has two common isotopes. One is U-235 and the other is U-238. So U-235 has number of protons 92 and number of neutrons are 143. Uranium 238 has number of neutrons 146. There is another example of carbon, carbon 12 and carbon 13. Okay, so we'll be taking on this discussion to radioactive level, where we'll be discussing the three types of radiations and what are the number of protons and neutrons in that, okay, and how will they change an atom if a nucleus is making that radioactive emission. So we'll be discussing that in next discussion. Please subscribe the channel and like the video.